Projectile motion. Projectile motion involves an object that moves in a curved path or a curved trajectory in the shape of a parabola. We make the assumption that there is no air resistance. We also assume that the only force acting on the object is the force of gravity. In other words, the free fall acceleration g is constant over the range of motion and is directed downwards. Now projectile motion looks at two-dimensional motion with constant acceleration g that can be analyzed as a combination of two independent motions in the x and y direction. So in the x direction, there is no acceleration. So the formulas we are going to use are limited. What we know is that the velocity in the x direction is also equal to the initial velocity in the x direction because the velocity stays constant. There is no acceleration. And we know that velocity is equal to your displacement over your change in time. And now we know how to derive this equation from calculus. We also know, because there is no acceleration, and I've already written it down here, but that your initial velocity is equal to your final velocity in the x direction. Now, in the y direction, there is a constant acceleration. It's called the acceleration due to gravity. It is constant. So we have several formulas we can use, the kinematics equations, in the y direction. So let's write those out now. So the first equation just looks at your average velocity in the y direction if you have a constant acceleration. Here's your second equation that you can use. So here's the last three equations that you can use. And notice, hopefully these look familiar to you. The acceleration values have been replaced with the small symbol g for acceleration due to gravity. And these, again, are only dealing in the y direction or the vertical direction. And we have talked about in Chapter 2 deriving equations from calculus, and these are the three we should know how to derive from calculus. Okay, so now that we know the ground rules and the equations we can use, let's investigate this a little bit further. Imagine we have some object like a football or soccer ball, and it's being kicked from the ground, and it follows this trajectory that I've colored here in black. Now the ball will be moving from left to right, so the initial velocity here will be at this point. Approximately halfway up, if we draw a tangent to that point, it would look like this. And I'm calling this v sub 1. At the very top of the trajectory, we will have a velocity which I'm going to call v sub 2. Notice that it's only horizontal in direction. This next point, approximately halfway down, has this vector. And lastly, when the object hits the ground, it has this vector, which I'm calling v4. Each of these vectors can be resolved into components, a horizontal component and a vertical component. And my initial velocity, my horizontal component, is called v sub naught x. My vertical component is v sub naught y. So each of these vectors resolved into components here, that's shown in red. Notice v sub 2. It's only going in one direction, only the horizontal direction. So at v sub 2, the speed that we're interested in is only the v2x. There is no v2y. Now in each of these cases there is an angle that we would be interested in, except for V2. And each of these angles will be different, and we will use them in our equations. The first one with the initial velocity, we're going to call that theta sub naught. The second one would be called theta sub 1, and so on. So how can we represent these components in terms of the vectors? So the red values in terms of the purple values. So I want to start with v sub naught x, and we're going to use a little bit of trig. Turns out if I took v sub naught x and divided by the hypotenuse, which is v sub naught, that is equal to something called cosine theta sub naught. Rearranging this equation for v sub naught x, I get that's equal to v sub naught cosine of theta sub naught. So what about v sub naught y? If I divide that by the hypotenuse, v sub naught, that's equivalent to sine of theta sub naught. Or solving for v sub naught y, that would give me v sub naught sine of theta sub naught. So here are two more formulas we can use when we're using projectile motion. Another thing I know with projectile motion are the times. So we're going to look at our motion in the x direction independently from the y direction, but one of the things we can set equal to each other are the time values. So if I could find the change in time in the x direction, I can set that equal to the change in time in the y direction. And really what we're just going to call that is the change in time. Okay, I want to talk with you again a little bit more about what I call my v sub naught x, or my initial velocity in the x direction. Now, just above this, we already saw that that's equivalent to v sub naught cosine of theta sub naught. But as you recall, because there is no acceleration in the x direction, that's the same thing as just v sub x, which is also equal to our displacement over our time. And lastly, because we are looking at motion in two dimensions independently, the x direction and the y direction independently, what we're going to do is use vector math. So for example, say I wanted to know v sub 1 in the previous drawing, or the drawing up above. Well, if I could know what the velocity was for object 1 in the y direction, and I knew the velocity of object 1 in the x direction, I can use my vector math to find that. So it turns out that's equal to the square root of my velocity 1 in the x direction, was just velocity x, because velocity x is the same everywhere. We're going to square that, plus my velocity 1 in the y direction. And then what we can do is just take the absolute value of both sides to find the magnitude. Now the direction, what I would call theta sub 1, is actually equal to the inverse tangent of my v1y divided by my v1x, which is just vx, and that will give me my direction. So this top value here is your magnitude, and this bottom value here, this is your direction. Alright, so let's talk about a special case where we can use some special formulas. So in this special case, a projectile is launched and it returns to the same horizontal level. This happens, for example, in several sports such as football and soccer and many others. So in this example, the ball is kicked from left to right. It does have an initial velocity here, which I'll write as such. There is some angle here, which I call theta sub naught. There is a peak height of this object's trajectory, which I like to call h sub max. At the peak or the top of its flight, there is only the horizontal component of speed, which I like to call v sub x. There is what I call the range, which is the maximum horizontal displacement. So some people may call it delta x. For these new equations I want to tell you, we're going to call it r for the range. And real quick on this side, we'll go ahead and assign direction. So plus x this way, plus y will be up. So your first equation here can be used to find your maximum height here in this trajectory. Notice that this equation is not on your formula sheet, but you should memorize it or put it in your graphing calculator. So your h sub max is equal to your v sub naught squared multiplied by sine squared theta sub naught all over 2g. There is another equation, and that is for your range. And this is the other equation for your range that you need to memorize or put in your calculator because it's not on the formula sheet. And your range is equal to v sub naught squared multiplied by sine of 2 theta sub naught all over g. All right, let's do an example. So we have some object, perhaps a football that is kicked. It has an initial velocity. It's kicked at some angle above the ground or above the horizontal. And the question is, what is the range of this ball and what is the maximum height the ball reaches in its trajectory? So we have some givens here. The initial velocity is 11.0 meters per second at an angle of 20 degrees above the ground. The acceleration in the x direction is 0, and the acceleration in the y direction is just the acceleration due to gravity g, which is equivalent to negative 9.8 meters per second squared if we assign up as positive. So for the first part, what is the range? We know we have a range formula that looks like this. And we simply plug in the numbers. I have a correction here that I'd like to talk about. In plugging in my value for g, I realize my g value is going to be positive. We're going to plug in a positive 9.8 meters per second squared. You could even plug in a positive 10 if you like. And that reason for that is that negative 9.8 has already been taken care of in the derivation of this formula, which you are not responsible to know about. But if it is in your book, if you're interested in looking at that on page 86 to find out why that negative goes away. But when we use this equation, then we will be plugging in a positive 9.8 meters per second squared. And in doing so, we get a range value of 7.94 meters. And our next question is, what is the maximum height of the object's trajectory? Here is the formula we are going to use for that. Here we're plugging in the numbers. And just as a side note, you want to make sure your calculator is in degrees. And here is your answer. Okay, let's try another example. Example 2. So we have some sort of an object that's rolling across a cliff with some initial horizontal speed. The object shoots off the cliff, if you will, and follows this trajectory that I've shown in the diagram. In this diagram, there is a height above the ground, which I'm representing as delta y. There is a horizontal displacement from the cliff, which I'm going to call delta x. There is an initial velocity of this object. Right when it comes off the cliff, we're going to call that v sub naught. Let's plug in some values here. We're going to call delta y equal to 1.0 meters. We're going to call my initial velocity 0.10 meters per second. Notice that this is the same thing as my initial horizontal velocity, which is the same thing as my horizontal velocity because it's the same everywhere. There's no acceleration in the x direction. Let's write that down. my acceleration in the x direction is 0 meters per second squared. My acceleration in the y direction is g, and that is negative 9.8 meters per second squared, which I'm going to round as negative 10 meters per second squared. There's another piece of information that is implied, and that is if this object comes off with only an initial horizontal velocity, then what is my v sub naught y? What is my initial speed in the y direction? And the answer is that is 0 meters per second. If my delta y is going to be 1.0 meters, then my 0 meters starts at the ground and my 1.0 meter will be up where the cliff is. I want to talk with you about my delta y a little bit more. So let's review what delta y is. Delta y is your change in your vertical position, which is your final minus your initial. And in this case, what is my final position? When the ball falls vertically in the vertical condition, the final position will be 0 meters. And when it initially starts off, when it comes off the cliff, it starts at 1.0 meters. So my delta y is actually going to be negative 1.0 meters. That negative indicates that the ball is moving in a negative direction. In this case, we could say falling down in the y direction. So I need to go back up to my given and make sure I put in a negative there for delta y. So I'm going to change my delta y in my given to make sure that it reflects the negative. So for my delta y here, I'm going to have a negative 1.0 meters. So for part A, what we want to find is what is the delta x of this object? How far away from the cliff does this object hit the ground? What is delta x? The formula that we're going to use is going to be v sub x is equal to delta x over delta t. Keep in mind, we know how to derive this equation now using calculus, so let's just review that briefly. We actually know that your instantaneous velocity is equal to dx over dt. By separation of variables, we multiply both sides by dt. Then we write v dt is equal to dx. Integrate both sides. We get v t, we're going to evaluate this, is equal to x, and we're going to evaluate that. Now, if we're using our definite integrals, we need to plug in our upper limits and our lower limits. This would be tf, ti, tf. Excuse me, this one here is x sub I, x sub f, x sub I, x sub f. And so by evaluating, I'm going to plug in my tf for t. I get tf, and I'm going to subtract by my lower limit, here t sub I. That's going to be equal to my x sub f minus x sub I. Just plugging in my upper and my lower limits for my function here. And we could write this then as v multiplied by delta t is equal to delta x, or v is equal to delta x over delta t. We actually want to use this form of the equation because we want to solve for delta x. Remember, this is v sub x here, and we could have this all throughout the equation, the derivation process if we wanted. We didn't need to drop that subscript here. Okay, so what are we given? So do we have v sub x? And yes, we do. So that's no problem. The problem here is we do not have delta t. So we need another equation to find delta t. This is the equation we're going to use to find delta t, but of course we aren't going to start here. We're actually going to start with calculus. So let's go ahead and derive this equation using calculus. We are again going to start with our v sub x is equal, that's our instantaneous velocity, is equal to dx over dt. We're going to separate the variables by multiplying both sides by dt. Those cancel. And I get v sub x is equal to, v sub x dt is equal to dx. We are going to integrate both sides. In doing so, though, I'm going to plug in another equation for v sub x. And actually, let me also do one other thing here. Since we are now talking about the y direction, is it okay to change our subscripts to y's? And yes, I think we should. So let's do that. Let's change our subscripts to y's here. Okay, that's better. Now we're looking in terms of y. Now we're going to plug an equation for v sub naught y right over here. So let's just review for a moment. There is another kinematics equation that looks like this. There we go. Now we're going to plug in this part of the equation, the v sub naught y at, in for v sub y. So let's do that now. So here it is. I'm going to rewrite this on another page because we're running out of room, and we will continue. All right, let's expand the left side of the equation a little bit here. So we get v sub naught y dt plus the integral of at dt is equal to the integral of dy. Let's make sure we have our upper and lower limits. All right, let's integrate this. So my first term will be v sub naught y t plus 1/2 at squared, and that'll be equal to y. So by evaluating, we get v sub naught delta t plus 1/2 a delta t squared is equal to delta y. And this is the equation we wanted to use. So now that we've derived our equation, we can now plug in our numbers. My delta y, if you recall, was a negative 1 meter. My v sub naught y is 0 because it only has an initial horizontal speed. We have a delta t, which we are solving for, plus 1/2 multiplied by negative 10 value for g, and then delta t squared. Luckily, the term with the initial velocity in the y direction goes away, and so we have this expression. Solving for delta t, I'm going to have it equal to the square root of 1/5 or 0.20 seconds squared. So I end up getting a value of 0.45 seconds rounded to two significant figures. Now remember, going back to one of my original equations, I want to plug this 0.45 seconds in to get my answer. That original equation was, just if you can recall, is that delta x, which I'm solving for, is equal to that horizontal velocity, which remains constant, that we already know, multiplied by my change in time, which I just found. So plugging in the numbers, I get an answer of 0.045 meters. Woohoo! Now there is a part B to this, and part B says, what is the magnitude and the direction of the object the moment it hits the ground? So what is V? Now, because v is a vector, velocity is a vector, we should have a magnitude answer and a direction. So let's go back to the picture. Let me redraw it here. The v I'm interested here is the moment when it hits the ground. And what I'm going to do is resolve this v into components. We'll do that with the color red. So we have a Vx and a Vy. We also need an angle, and the angle that I'm interested in is right here. This is the angle that I'm interested in. This is going to be my theta. Turns out that's the same thing as this angle right here. So we're going to use trig to find that angle. If you recall from vector math or even the Pythagorean theorem, my v, the magnitude of that, is just going to be the square root of my v sub x squared plus my v sub y squared. What's really nice is my v sub x is just my horizontal component, which stays the same throughout, and that one I already know, it's given. The one I do not know, though, is the v sub y, so we need another equation to find v sub y. So this is my equation to find v sub y. Luckily, I have everything. I have my v sub naught y, which is 0. There is no initial speed in the y direction. My a value is just my acceleration due to gravity, or g. And then my time I already found in part A. We just have one little thing to do, and that is to derive this equation using calculus. So let's do that now. In deriving this equation, we have an instantaneous acceleration is equal to a dv dt. By separation of variables, we're going to multiply both sides by dt, cancel that out on the right-hand side, and I now have an equation of a dt is equal to dv. We're going to integrate both sides, and I get at is equal to v. By plugging in my upper and lower limits, I get a delta t is equal to delta f, or I get vy is equal to v sub naught y plus a delta t. Yay. Okay, so now we're ready to plug into our equation. Let's bring this down here. And my v sub y is going to be 0 plus a negative 10 plus my time of 0.45 seconds from the previous part of the problem. So my v sub y is going to be negative 4.5 meters per second. Is negative appropriate here? And the answer is yes. The object is moving in a negative direction, in a negative y direction at this point. So going back to the ultimate task at hand, we're going to start by finding the magnitude of v the moment the object hits the ground. We're going to plug in our horizontal speed, which was given initially. So we're going to plug in that, which was 0.1. And my vy, which I found to be negative 4.5 meters per second squared, the whole value squared. And in doing that, I get my speed value of. So here is your magnitude. But what's the direction? The direction is going to be equal to this angle that I want to solve for, which is the inverse tangent of my v sub y over my v sub x. So my angle is my inverse tangent of my negative 4.5 divided by 0.1, and that ends up being the angle of negative 88.7. So again, let me repeat here. It's equal to negative 88.7 degrees. Now this negative indicates below the horizontal. Here is your practice, and good luck.